What's up, mathematicians? Welcome back to our lesson on logic and knowing. In the last video, I talked about how logic is a tool we can use to know things with certainty and to generate new knowledge. I want to start this video by asking a question. And let me pull it up here. What does it feel like to know something? The experience of knowing something with certainty has a feeling attached to it. What is that feeling? That might seem like a strange question to ask because, you might be used to thinking that logic and being certain about something shouldn't have anything to do with feelings, since we're often told that feelings are not reliable. In fact, we are taught implicitly or explicitly that math and logic are objective and true in some absolute way, while feelings are subjective, ephemeral, and relative to our own experiences and perspectives. But in my opinion, there's a real problem with this way of thinking. If you don't know what it feels like to know something, then how will you ever know if you know something? Feelings are a central part of the human experience, and we shouldn't try to divorce our experience of doing mathematics from our feelings. That would make doing mathematics feel inhuman. It's common for students to think and feel that they don't know with certainty if they're correct about some problem or proof, and that it is the teacher who is the arbiter of what is true and correct. And the teacher checks your answer and tells you if you're right or wrong. And by the way, I do think that sometimes teachers and professors are a bit too stingy about this feeling of what it's like to know something. Maybe have this idea that you need all the proper training and then you can, determine whether your solution is right or wrong. But of course, it's actually much better if students can determine for themselves if what they're doing is right or wrong, which is a skill, by the way, that takes time. Personally, it's a skill that I'm still developing after all my years of teaching, right? I don't always know if an understanding or insight that I have is correct. But I think that part of learning to make this determination of knowing whether you are understanding something with clarity, is knowing what it feels like to really know something. What does it feel like to have understanding and insight and clarity? One of my personal definitions, a definition that I like for mathematics is this. Mathematics is the search for clarity. Okay, and maybe that doesn't seem like so much a definition as a description of the experience of doing mathematics, but I do think it captures something about the essence of what mathematics is all about, at least as far as the human endeavor of mathematics. And there is a feeling, an emotional experience, if you will, that comes with finding this clarity. So in this video, I want to explore what it feels like to know something, to experience clarity. Of course, since we're talking about feeling and experience here, I can't just tell you about it. That won't do any good at all, right? I have to try and show you so that you can experience the feeling for yourself. So we'll look at several problems that I think can give you a taste of what this feeling is like. I'm not going to show you the solutions in this video because I want you to wrestle with the problems and experience what the clarity of coming up upon a correct solution feels like. Okay, so the first of these three problems involves magnetic rods. Okay, so you can see here an arrangement of three magnetic rods. And if you have three magnetic rods, it's pretty easy to arrange them so each point is lined up, as you can see right here. However, I can also do an alternate arrangement where these 2 points are not lined up and this third point is. My question to you is this: is it possible to take these three rods and arrange them in such a way, I don't know what it might look like, but well, actually I do know, but anyway, The point is, can you find a way to arrange these 3 rods so that all 3 points would not be mismatched, as you can see here and here, rather than just 2 of them? And also prove that you're correct, right? So prove that it is possible by demonstrating an arrangement, or prove that it is not possible. And once you've done that, I would encourage you to think about the case where maybe you have 4 magnetic rods, or 5 or 6. You know, which, if any, numbers is it possible to have this mismatching at every corner, at every vertex? And which, if any, numbers is it not possible to have mismatchings at every vertex? Okay, so that's the first problem. The second problem, let's see, I gotta come back. Let's see, right here we go. The second problem is this one right here. Okay, it's a problem with gears. Now you can see an arrangement of gears right here. And what I want you to think about is, what if you tried to turn, and imagine, you know, they're like fixed in a way that if they were separate, they would freely turn around some fixed point, right? But given the arrangement here, imagine you tried to turn one of the gears. What would happen? Would it turn? Would they all turn? What direction would they turn in? And moreover, what if you change the number of gears, right? You can count how many there are here. What if there were more or fewer gears? Generalize what would happen with different numbers of gears, and try to come up with a proof to show what you have discovered is correct. Now, for the third problem, this is actually my favorite one of the 3, and it's based around a game. Okay, so if possible, go find someone else to play this game with. If you can't find someone else, if you don't have someone willing or around to play it with you, then you can play it by yourself and move for both players. But I think it's much better if you play with somebody else and you can discuss it. And let's see, I actually zoom this out a little bit. All right. Well, this is the only chessboard that I happen to have at my house, and this is what you want to do. Get a chessboard or a checkerboard, or print one off using the link below in the description. And then get 2 coins or small rocks or some similar objects like this, and 31 paper clips or dominoes or similar oblong objects. Once you have those things, you have a checkerboard, you have the coins, you have the paper clips, or whatever similar objects are going to work. The rules are as follows. First, player 1 will take the 2 coins and place 1 coin, place each on a square. So I'll place one over there. I'll place another one over here. Why not? So there we go. At this point, player 1 is done. Now it's up to player 2 to take the paper clips and try to cover the entire board by having each paper clip cover 2 squares, kind of like this. Okay, and obviously I don't have enough paper clips here to do it, and I'm not here to show you if it's possible or not possible with this arrangement. But the point is, if player 2 can arrange the paper clips so that all the squares on the board are covered, player 2 wins. If player 2 is unable to find an arrangement like this, where all the squares are covered with the paper clips, then player 1 will win. And by the way, you're not allowed to cover diagonally, right? So you can cover 2 squares like this or 2 squares like this, but not diagonally. Okay, so those are the rules. And go ahead and play the game until you can determine a winning strategy for one of the players. And then prove that it is a winning strategy. Prove that player 1 can always win by doing this, or player 2 can always win by doing this. Okay, so again, I won't be giving the solutions in this particular video. Spend some time wrestling with these problems, searching for the insight that will make the solution clear. And by the way, if you're stuck, that's okay. Being stuck is actually a great place to be. Most math researchers, the people who are actively creating new mathematics, spend the vast majority of their time being stuck. if you're never stuck, you will never have any real breakthroughs, right? You'll miss out on those amazing moments of clarity. It's when you're stuck that you can be creative, you can play around, you can try new things, and maybe you'll get to experience that feeling of having an insight, of making a breakthrough, and see what that feeling is like. So if you are stuck, take a break, go do something else, and come back to the problem later. Sometimes insight and understanding just take some time. I do plan to make another video discussing the solutions, but if you watch that video without wrestling with the problems, you won't get that same feeling that comes with a flash of insight or a moment of clarity. And it's the feeling that we're looking for here, not the solution to the problem. A few years ago, I thought I'd share, I had a student who was actually working on the checkerboard, the version of the checkerboard problem that will appear in the practice problems for this lesson. And when the insight came to her, she involuntarily exclaimed out loud, which she said was actually a little embarrassing since she was in a public place. But that is the power of a feeling. That would never happen if solving the problem and experiencing the clarity that came with it were purely a rational thing. So it's this feeling that we want to try to get to know a little better. The feeling of what it's like to know something with certainty, to experience the clarity that comes from insight and understanding. Okay, so that will wrap up this video. In the next lesson, we will look at the difference between deductive and inductive logic. Hope you're looking forward to that. Thank you so much for watching. We'll see you in the next video. Bye-bye.